Welcome, deep divers. Tonight, we're going on, well, quite an extraordinary journey.
Absolutely. We're starting with the sheer scale of it all.
Yeah, the universe. It's just mind-bogglingly vast. I mean, take our own Milky Way galaxy, our closest major neighbor, Andromeda. It's about 2.5 million light years away.
2.5 million. That number. It's hard to even wrap your head around.
It really is. And just to try and put that into perspective, imagine you hop aboard a typical spacecraft.
Okay, like the ones we use now.
Exactly. Maybe cruising at, say, 28,000 kilometers per hour.
A decent clip for us, but cosmically.
Right. To reach Andromeda at that speed, you'd be looking at something like 94.5 billion years.
Billion, wow. That's, yeah, practically forever.
And even if we could hit the absolute speed limit, the speed of light...
Which we can't, but hypothetically.
Hypothetically, yeah. It would still take 2.5 million years.
So it really makes you feel stuck, doesn't it? Trapped by these enormous distances.
It does. But what if there was, a shortcut?
The cosmic shortcut idea.
Exactly. A way to jump across those millions of light years, maybe not in billions of years, but in months, or dare I say minutes.
Well, that's the fascinating part. This idea, these wormholes, they aren't just science fiction anymore.
Like in the movie Interstellar, I remember that. They used a wormhole near Saturn.
Precisely. And while that was fiction, of course, the concept itself, it's actually based on real science, rooted in, well, some very deep physics.
Okay, so let's dive into that. These wormholes. What's the actual science? How could they possibly exist?
Right. To really get it, you have to start with the foundation. And that means going back to Albert Einstein.
His theory of relativity.
That's the one. Specifically his field equations. He first presented them way back in 1915, over a century ago.
And they're still central to understanding things like this.
Absolutely fundamental. In simple terms, these equations, they describe how matter and energy influence space-time, how they curve it.
The famous fabric of space-time idea.
Exactly. Einstein liked to visualize it as a big stretchy mesh. You put something heavy on it, like a planet or a star.
It makes a dip, a curve.
Right, and the heavier the object, the stronger its gravity, the deeper the curve it makes in space-time.
And what's amazing, I read that Einstein himself, he couldn't actually solve his own equations fully, only for a specific case.
That's true. They are incredibly complex. 10 nonlinear partial differential equations, often sort of bundled into one representation. He gave an approximate solution.
So who cracked them first?
That was Carl Schwarzschild, just a year later, in 1916. He found the first exact solution.
And that was important because...
Hugely important. Schwarzschild's solution gave us the mathematics behind the concept of a singularity, that point of infinite density and gravity.
Which points towards black holes.
Directly. It theoretically proved their existence almost 100 years before we actually managed to photograph one in 2019. Quite incredible.
Okay, so black holes came out of solving Einstein's equations. How does this connect back to the wormhole shortcuts?
Well, here's the key insight. Black holes were one possible solution to those complex field equations. But just like, simple quadratic equations in school can have more than one answer.
Right, like x could be 2 or 3.
Exactly. Einstein's much, much more complex equations can have many potential solutions. And wormholes, they represent another valid mathematical solution.
I see. So it's not just black holes. The math allows for other weird things, too.
Precisely. And the specific solution for a wormhole actually has a name, the Einstein-Rosen bridge.
Named after
Albert Einstein and his assistant, Nathan Rosen. They discovered this particular solution together back in 1935.
So an Einstein-Rosen bridge, a wormhole, basically a tunnel, a shortcut through space-time.
That's the concept. Let's try that classic analogy to make it clear. Imagine you've got a flat sheet of paper. That's like our 2D space.
Okay.
Put 2 dots on it, A and B. The shortest way between them is just a straight line across the paper.
Makes sense.
But now, if you could bend the paper, fold it over using a third dimension.
So points A and B are suddenly much closer, right next to each other, just separated by the folded space.
Exactly. And if you could then poke a hole directly through from A to B.
That's a shortcut. Much shorter than going all the way across the flat surface.
That's the idea. Now, imagine applying that to our actual 3D space. The path from us to Andromeda seems like 2.5 million light years in a straight line.
The long way around.
Right. But what if our 3D space could somehow be bent or folded through a fourth spatial dimension? Something we can't easily visualize.
Then maybe a much shorter path, a hole through that higher dimension, could connect those two distant points.
That's the possibility the Einstein-Rosen bridge represents. It's a bit like how airline flights work on Earth.
How so?
Well, if you look at a flat map, say Delhi to New York, the straight line looks shortest.
Right.
But planes fly a curved path over Greenland and the Arctic. On the 2D map, it looks longer, but on the 3D globe.
It's actually the shorter distance because the Earth is round.
Exactly. It's about understanding the true geometry. Wormholes are like that,
Yeah.
but involving space-time geometry and potentially higher dimensions.
So where did the name wormhole actually come from? It's more evocative than Einstein-Rosen bridge.
It is. That term came much later. In 1957, a physicist named John Wheeler was writing about these Einstein-Rosen bridges.
Okay.
And he used this great analogy. Imagine a worm on the surface of an apple. It could crawl all the way around the outside to get to the other side,
A long way.
or it could just eat a hole straight through the core, a shortcut.
The wormhole. That makes perfect sense.
And the name stuck. It's why when you search online, you often see those diagrams, right? The bent sheet of space-time with a kind of tunnel connecting 2 points.
Yeah, those are everywhere. Created by, what, intense gravity?
Supposedly, yes.
Yeah.
But it's important to remember those are just 2D representations. They help us grasp the concept, but they're limited.
So what would a real one look like if we could see it in our 3D space? Not a flat hole.
Probably not. Most physicists think it would appear more like a sphere, a sort of distortion in space.
A sphere, like a bubble.
Kind of. As you approached and entered it, the view would likely get incredibly warped. Things would appear intensely curved, and looking back, the space you just left might seem to recede in a weird, circular, swirling way.
Wow. Actually, the movie Interstellar did show it as a sphere, didn't it?
It did, and that depiction is generally considered quite plausible, scientifically speaking. It gave a good sense of that visual mind-bending aspect.
Okay, so theoretically, mathematically, they're possible. There's solutions to Einstein's equations. But the big question, can we actually use them? Can humans travel through one?
Now we get to the practical problems, and there are quite a few.
I bet. Let's start with the first hurdle. How do you even open one? You mentioned extreme gravity. Where does that come from?
Well, according to the original Einstein-Rosen theory, the only things we know of with enough gravitational pull to potentially create such a space-time tunnel are black holes.
Right, we talked about them being a solution too. So you need a black hole to open the entrance.
That's the idea. But here's the massive catch, the real problem. If the entrance is a black hole, what's the exit?
If the exit is also a black hole,
Then it's not a tunnel, it's a trap. Anything that goes in gets crushed. There's no coming out. It's a one-way trip to oblivion.
Okay, that's not ideal for interstellar travel. So for a traversable wormhole, one you could actually go through and come out somewhere else.
You'd need the exit to be something totally different. Something, well, the exact opposite of a black hole.
Opposite of a black hole, what would that even be?
That brings us to another purely theoretical but fascinating concept. The white hole.
A white hole?
Yes. It's another potential solution that pops out of Einstein's field equations. And it's imagined as the complete inverse of a black hole in, like, every way.
How so? What are its properties?
Okay, so with a black hole, once something crosses the event horizon, its point of no return, it can't escape. Not even light. A white hole is the opposite. Nothing from the outside can enter its event horizon. Matter and light can only leave it, flowing outwards.
So it would be incredibly bright, constantly spitting things out.
Theoretically, yes. Extremely luminous. The term white hole itself was actually coined by a Russian physicist, Igor Novikov, back in 1964.
So a black hole's event horizon is no exit, and a white hole's is no entry.
You got it, a boundary of no admission. Stuff inside can get out and affect the universe, but nothing outside can ever get in. It really messes with our intuition.
It absolutely does. Okay, but how would one form? Black holes come from collapsing stars. You can't really run that process in reverse, can you?
That's a huge question mark, and one of the main reasons they remain so theoretical, their formation mechanism is tricky.
Are there any ideas?
A few, quite speculative ones. Some scientists propose that maybe the Big Bang itself, the origin of our universe, could have been something like a primordial white hole exploding outwards.
Wow, okay. What else?
Another idea connects to Stephen Hawking's work on black hole evaporation.
Where black holes aren't actually permanent, they slowly radiate away.
Exactly, over immense time scales. This links up with a concept in quantum physics called the no-hiding theorem. Basically, information can't be truly destroyed.
Okay.
So, the thinking goes, if a black hole sucks in all this matter and information, and then eventually evaporates, where does that information go?
It has to come out somewhere.
Perhaps Maybe, just maybe, when a black hole finally dies, the information is released through a white hole, a kind of information recycling system for the universe. Highly speculative, of course.
Highly. But are there arguments against white holes? Reasons to think they can't exist?
Oh, definitely. And strong ones.
Yeah.
The main one comes down to thermodynamics, specifically the second law.
Entropy. The idea that disorder always increases.
Precisely. Entropy in an isolated system can't decrease. Think about shredding paper. Easy to increase disorder, impossible to perfectly reverse it.
Right.
Black holes fit this perfectly. They increase entropy by gobbling up stars and planets, making things more disordered.
But a white hole spitting out organized matter
Would seem to decrease entropy locally, reversing that process. And according to the second law, that just shouldn't happen. It's a major conceptual hurdle.
So thermodynamics seems to argue against them, but you know science, people always look for loopholes or exceptions. Is there any hint they might exist, despite the theory?
Well, there was one very curious event. It's often brought up, though it's far from proof. Back on June 14th, 2006,
What happened?
the Neil Gehrels Swift Observatory, a space telescope, detected something called GRB 060613. It was a gamma ray burst, a massive sudden flash of high-energy light.
Okay, gamma ray bursts happen, right? Usually from supernovae or merging neutron stars.
They do. But the strange thing about this burst was its location. It happened in a region of space where there's no sign of a star collapsing or anything that would typically cause such a burst. Just empty space, seemingly.
So a huge explosion of light from nowhere.
Essentially. Which led some astronomers to speculate, very cautiously, could this have been a white hole suddenly releasing a burst of energy?
Huh, interesting. But just one event.
Just one, never repeated. So it remains a complete unknown. White holes are firmly in the theoretical maybe category. But then again,
Black holes were purely theoretical for decades too, right? Until we found the evidence.
exactly. It's a good reminder that absence of evidence isn't always evidence of absence, especially in cosmology. The universe keeps surprising us.
Definitely. Okay, so gravitational wormholes connecting black holes and maybe white holes, still very much out there in theory land.
There now, yes.
But it's fascinating that the principle behind creating shortcuts, manipulating fields, that's actually been done, right? Just not with gravity.
You're talking about the magnetic wormhole experiment.
Yeah, that was in 2015, wasn't it? Scientists made one in the lab.
They did, and it was a very clever piece of work. They weren't manipulating space-time or gravity, of course. They were manipulating a magnetic field.
How did they do it?
They used special materials, metamaterials, and superconductors,
Yeah.
specifically yttrium, barium, copper oxide, cooled way down with liquid nitrogen. And with this setup, they managed to essentially take a magnetic field, make it enter one point, guide it along an invisible path around a central region, and have it emerge from another point as if it had tunneled through.
So they created a path where the magnetic field existed, but it was undetectable in the space between the entry and exit points.
Exactly. They effectively made the magnetic field take a shortcut, invisible to the outside, through their device. It acted like a wormhole, but for magnetism.
That's really cool. Obviously not for travel, but it shows the core concept. Bending a field to create a shortcut isn't totally crazy.
Precisely. It demonstrates that the underlying physics of creating these kinds of tunnels or shortcuts through field manipulation is sound, at least in principle, even if applying it to space-time gravity is a whole different, much harder challenge.
So besides wormholes, are there other ideas from Einstein's work about faster than light travel? Any other theoretical shortcuts?
There are. Another famous one that also comes out of general relativity is the Alcubierre Drive.
The warp drive, like Star Trek.
Sort of, yeah. It was proposed by Miguel Alcubierre, a theoretical physicist, back in 1994.
And how does that supposedly work?
The key idea is that the spacecraft itself doesn't travel faster than light through local space, because relativity forbids that.
Right, the cosmic speed limit.
Instead, the Alcubierre Drive would warp space-time around the ship. It would contract space-time in front of it.
Pulling the destination closer.
Effectively, yes.
Yeah.
And it would expand space-time behind it.
Pushing its starting point further away.
Exactly. So the ship rides within a warp bubble of normal space-time, but this bubble is moved through space-time by distorting space itself. Relative to distant points, the bubble could travel faster than light.
Surfing on a wave of space-time?
That's a good way to put it. And guess what?
Let me guess. It's another valid mathematical solution to Einstein's field equations.
You got it. It all comes back to Einstein. But just like traversable wormholes, there's a catch.
There's always a catch.
The Alcubierre Drive requires something called exotic matter. Matter with negative mass or negative energy density.
Stuff we've never seen and don't know if it exists.
Pretty much. So again, mathematically possible according to the equations, but requires ingredients that might not exist in our universe or that we don't know how to create or handle.
Still, it's just incredible thinking that these wild ideas, wormholes, warp drives, things that feel like pure science fiction, are actually rooted so deeply in equations Einstein wrote down over 100 years ago.
It really is astounding. His work didn't just describe the universe we knew, it opened up possibilities for things we haven't even discovered yet. It laid the theoretical groundwork for potentially traversing this vast cosmos.
Absolutely. So the big takeaway here seems to be, the universe is almost unimaginably huge.
No doubt about that.
But our understanding of the fundamental rules, like Einstein's relativity, keeps hinting at these, well, mind-bending ways we might one day overcome those distances.
From the theory of wormholes and white holes to that actual magnetic wormhole in the lab, even at concepts like the Alcubierre Drive, the exploration, theoretically at least, continues.
So what stands out to you listening to this? For me, it's that reminder that even if we haven't actually seen a gravitational wormhole or a white hole, the scientific chase is constantly pushing the boundaries of what we think is possible.
And it really forces us to ask some big questions. If any of these concepts, traversable wormholes, warp drives, ever become reality, what does that mean for humanity? For our future out there among the stars?
Yeah, how does it change our place in the universe? Are we destined to be cosmic explorers hopping between galaxies?
It's a profound thought.
It really is. So here's something to mull over. Imagine a future where these aren't just equations. Imagine stepping onto a ship or even through a portal knowing it's an Einstein-Rosen bridge. What wonders, what entirely new realities, or maybe even what unsettling truths might we find waiting on the other side?